Okay, so we're going to continue talking about handle decompositions, and particularly we're going to talk about handle moves and what we can do to transform the handle body decomposition. So let me recall our setup. So we had X, which was, let me assume it's a closed manifold, but you can, if you want to look at a compact manifold with boundary, you have to put the extra condition on the boundary, which is that the function attains its maximum, all the critical points are in the interior. It always equals the maximum on the boundary, but I'm not going to bother with that right now. So we fix a closed manifold and say that we have a Morse function with the property that each critical value corresponds to a unique critical point. So the number of points, the number of pre-images of a critical value, f of p is equal to 1 for every critical point. Okay. So each critical value corresponds to a unique critical point. So now we fix a gradient-like vector field. So let V be a gradient-like vector field. So then we obtain a handle decomposition of X. So what is a handle decomposition? It's basically a decomposition of X into a increasing sequence of manifolds with boundary, that a finite sequence of manifolds with boundary. So i.e. there exists manifolds with boundary. So you start from the empty set, and then you have x1, then you have x2, etc. until, say, xm, which is your x itself, where xi plus 1 is obtained from xi by attaching a handle. And the point is actually this decomposition of x1, x2 through xm doesn't actually depend on the gradient-like vector field. It only depends on the function, on the Morse function. And by the way, the gradient-like vector field is 4f. So let me recall quickly how what this means and how this depends on the gradient-like vector field. So we choose, so let P1 through Pm minus 1 be the critical points of F ordered by F. So they're ordered by their images. And let A1 through AM be real numbers such that, so F of P1 is less than A1, is less than F of P2, is less than A2, etc. So they intertwine with, no, so, sorry, it's M critical points. F of PM less than AM. Okay. So then, of course, basically we defined xi to be just the pre-image of minus infinity AI, which we defined to be this X AI. We had already defined this, so maybe I won't put the column. Okay. So anyway, this the sequence of manifold with boundary only depends on the Morse function. And we showed that, you know, basically this up to the diffeomorphism type, it doesn't depend, these xi's, they don't really depend on the fixed, on which AI you choose. You just, as long as you choose some value in between two critical values, you have the same manifold up to the diffeomorphism. Okay, so the question is, how does V specify the handle attachment? So, oops. Okay, so to talk about the handle attachment, I mean, I kind of already talked about this in some different ways, but let me define these unstable manifolds and stable manifolds, because I think this maybe will be a little clearer. So let phi t be the flow of V. And actually, I want to assume, for simplicity, that V is the gradient of F near the critical points for a Euclidean Riemannian metric in a Morse chart. So that just means, you know, that there exists a Morse chart. So i.e., there exists a Morse chart near each critical point such that V is equal to 2 minus 2x1 ddx1 minus 2 xk ddxk plus 2xk plus 1 ddxk plus 1 plus 2xn ddxn. Okay, so this is not true of every gradient-like vector field in general, the way I defined it, but some people define it this way. And if you allow for a general gradient-like vector field, you have to use a little bit more analysis to show some of the things that we want to show. But if you choose this kind, it doesn't actually matter. You can get all the transversality that you want, even if you fix this behavior of V near the critical points. Okay, so anyway, now let phi t be the flow of V, and we can define, so for a critical point, for the critical point of F, we define the unstable manifold and the stable manifold of P. So the unstable manifold, and it depends on V, this is the set of points in X such that the limit of the flow as t goes to plus infinity is equal to P. This is called the unstable manifold, sometimes called the the descending manifold. And the stable manifold is the set of points such that the limit as t goes to minus infinity equals P. This is called sometimes the ascending manifold. Okay, so let's look at an example. So let's look at our heart Morse function on S2. This is the heart. And as usual, if I draw a surface embedded in R3, I'm thinking of the Morse function as just being the height. Okay, so I'm not going to write that. So I have 4 critical points. 1, 2, 3, 4. So let me call this P, Q, R. S is not good, and U. No, U is also not good. W. Okay. So let's look at what the unstable manifolds and stable manifolds are of these guys. So if I look at the unstable manifold of P, and my V here is just going to be the gradient of F with respect to the Euclidean metric on R3. Did someone say anything? No, maybe someone just, someone raised a hand. No, maybe that was accidental. Did you have a question, Andres? No. Okay, maybe it was an accident. Okay, so wait, something? Oh, it was an accident. Okay. Yeah, you can talk. That's probably better because then I don't have to switch back and forth. Okay, so let's look at the unstable manifold of P. So these are the points here that flow to P as you go up, or as you go down, they flow out of P. Okay, so this is going to be, maybe I'm just going to draw. Probably better. So it's going to be like this. Okay, so it's this thing here. So all the points in here and on the back, it's a little disk. This is the unstable manifold of P. And the stable manifold of P is just the point P itself. Okay, so the things that basically flow towards P as you flow down, or they flow out of P as you flow up. Okay, and these names, unstable and stable, they're there. Maybe you're confused because of the direction of T, but usually people think about the downward flow. I didn't want to do that in this class, but if you think about the downward flow, unstable is what's flowing down, what's leaving the place as you flow down, and stable is what's converging to the point as you come up, as you flow down too. But anyway, maybe ascending and descending manifolds are a little make more sense. But I think you know what I'm talking about. So some very similar thing happens for Q. So for Q, I'm not going to write down because it's a similar story. So the unstable manifold of Q and the stable manifold of Q are analogous. For R, it gets interesting. It's a little bit more interesting. So the unstable manifold of R and the stable manifold of R. So the unstable manifold of R is going to be so this right here is R. And the stable manifold of R is this little ring here. Okay, so everybody sees. And then finally, for W, the unstable manifold of W is just the point W. And the stable manifold of W is basically, I'm going to write this. Okay, so you basically take your whole heart and you remove this segment here, and everything else flows to W. Okay. So any questions about this? Are the pictures, do the pictures speak for themselves?
Eu tenho uma pergunta.
Sim.
Eu acho que eu fiquei um pouco com dúvida com uma coisa que você falou na aula passada, talvez. Se a gente fala que elas não se intersectavam, parece que tipo, a variedade estável de W se intersecta com a variedade unstable de P.
Não, as variedades instáveis não se intersectam entre si, e as estáveis também não se intersectam entre si. Mas aí
Ah,
uma
tá.
estável e uma instável podem se intersectar, porque você está pensando no limite para ter mais infinito e menos infinito, right?
Ah, tá, tá, tá.
Yeah. No, in
Entendi.
general, the unstable and the stable manifolds of different critical points intersect. I mean, if you take the same point, the point, it's the critical point itself is in both the unstable and the stable manifold of itself. What I said last time is that the unstable manifolds don't intersect themselves, each other, and the stable manifolds don't intersect each other. Okay, but now, maybe I'll leave an exercise. It's kind of interesting. It's not very hard if you have that assumption on the gradient like vector field, which is that, so if the index of pi is k, then the unstable manifold of pi and the stable manifold of pi are diffeomorphic to open disks of dimension k and n minus k, respectively. Okay, so this exercise it's not very hard. I mean, you look at a neighborhood of the critical point, and you look at, the unstable manifold and the stable manifolds there. If your vector field has that standard behavior, then it's pretty easy. And then you just flow them out of that neighborhood using the flow of V, and you get the diffeomorphisms. Anyway, I told you how to solve the exercise. But I mean, I think it's instructive to see that this, what I just mentioned, is true for all these guys. Okay? And obviously, maybe it's not so obvious, but the open disk of dimension 0 is just a point. It's the same as the closed disk of dimension 0. Okay? And moreover, we have that these disks, this is going to intersect all the regular values transversely, but in particular, it's going to intersect the level, the pre-image of ai minus 1 transversely, and the stable manifold of pi intersects the pre-image of ai transversely. Okay, I mean, they will intersect everything transversely, but in particular these. But what is actually true is that now, what is this intersection? Because there are no other critical values, critical values between the value of pi and ai minus 1, then you can actually say that this intersection here is just going to be a sphere of the right dimension, and this guy here is also a sphere, but now the dimension is n minus k minus 1. Okay, so basically the picture that you have is, here is your pi, and then you have this disk. So this is a bk, and here you have your other disk, which is a bn minus k. So this is the stable manifold, and this is the unstable manifold. So when you intersect this with the level ai minus 1, then you get a sphere sk minus 1. And when you intersect this with the level ai, then you get a sphere Sn minus k minus 1. Okay? Any questions about this? All right, so the handle itself is just a neighborhood of the union of these two disks. So the k handle is a small, maybe closed neighborhood of the union of this disk, the unstable disk, with the, I mean, open disks is the same as open balls. Maybe I should just say balls. I don't know why people often talk about disks, but you know, the disk is the same as the ball. It's just a dimension convention. You look at the union of the unstable manifold with the stable manifold, and you intersect that with the pre-image of AI minus 1 AI. Okay, so the picture you should have, I mean, that two-dimensional picture that I had before, sort of this is your PI. This is the unstable manifold right here. This is the stable manifold right here. And then your handle is just something like this. Okay, and then as we saw before, you know, in two classes ago, and I kind of reviewed last time, apart from this, this interesting subset, this handle, the rest is just a diffeomorphism. So the rest, you can think about it either as attaching a cylindrical manifold, so you know what you have left on the boundary times an interval, you just add that, or you can collapse using the flow and think about this handle as collapsed a ball k times a ball n minus k, and you just smoothen the corners. But the point is that the vector field V determines this attaching map. So the attaching map, which is kind of the crux of the attaching the handle, so the attaching map is really just this map that goes from sk minus 1 into the boundary of xi, which is just given by, you know, how this sk minus 1 is diffeomorphic to the unstable manifold intersected with the pre-image of ai minus 1. So the attaching map is basically the map that takes sk minus 1 to this, which is the same in this picture of looking at this map right here. Okay, so it's looking at how the unstable manifold intersects with this regular value level where we're cutting the manifold. Okay, so that's the important map, and we know this is diffeomorphic to an sk minus 1, but this diffeomorphism is the definition of the attaching map, basically. Okay. But I mean, there's a little more, which is it's not just the embedding sk minus 1, but it's embedding sk minus 1 with a framing. So there is with a framing. So the framing is just telling you how to thicken it, basically. And this information is also contained in V. Okay.
Hello, sir.
Yes.
On the left side picture, with
Yeah.
the orange color, you wrote AI and AI minus 1.
Yeah.
Would not it be AI plus epsilon and AI minus epsilon?
It doesn't have to be. It doesn't have to be plus epsilon. It's not AI minus 1. It's AI minus 1, like this.
Oh, okay.
Yeah, so it's the index minus 1. So I mean, you can do minus epsilon plus epsilon, but it doesn't matter. You can actually go all the way down to. So I chose the AIs to be values that are in between the critical values. So there is no. The point is that there is no critical point between pi, between the value of pi and AI minus 1. I can take any one that I want. It doesn't have to be it doesn't have to be the value of pi minus epsilon. So AI is not the value of pi. AI is something bigger than the value of pi. Remember, we assume, you know, we define the AIs to be squeezed in between the values of the function. Okay.
Okay. Mhm.
All right. So
Sorry, can you explain again the drawing on the right?
yes,
What is the green part?
the green part is a neighborhood of. It's the K handle. It's a neighborhood of the union of the unstable manifold of Pi with the stable manifold of Pi.
Ah, okay.
And the point is, like, up to the diffeomorphism type, it doesn't matter which neighborhood you pick. You know, like, it could be a really, really small neighborhood, or it could be a bigger neighborhood. But the point is that outside of any of these neighborhoods, the flow is basically trivial. So you just have the cylindrical behavior. It's the R that I put before. So, yeah. And you know what I said also is, like, if you actually quotient by the flow here, and in the cylindrical part, sort of this whole thing here gets collapsed to the product of these two spheres.
Ah, okay, so it's the same drawing you did yesterday.
Yes.
Okay.
Yeah. It's easier to do drawing here than to do drawing with this picture here.
Yes, of course.
Yeah. Okay. But the point is, like, the only information that you actually get that's relevant for constructing the manifold from the vector field is you get this attaching map with a framing. So when you have an attaching map with a framing, that tells you everything you need to know to attach a handle up to the diffeomorphism, So sort of the point is that this V determines the attaching sphere. With a framing. So, you know, what's the attaching sphere is basically a map, an embedding from sk-1 to the boundary of the handle body xi-1. This is a framed embedding. Okay, the diffeomorphism type of xi is determined by psi. Okay. So I mean, there is a little bit of ambiguity when we talk about what exactly it means to attach a handle in terms of defining a manifold. But up to the diffeomorphism type of the manifold, it doesn't really matter. So V determines that. Okay, any questions? So now I want to talk a little bit more about handle slides. I said some stuff about it yesterday, but I think it was a little confusing. Maybe I want to say it a little bit more now. So a handle slide is a transformation of the way that you attach handles without changing the orders of anything and without even changing the Morse function. So a handle slide is just a way of changing, attaching maps without changing the Morse function, or even or without changing the order of the handles or the Morse function or anything. So you don't change the critical points, you don't change anything, but what you actually change is you change the gradient-like vector field. So how does it work? Well, it's actually very simple from the point of view of attaching handles. All that you're doing is you're taking an isotopy, you take your original embedding for a certain, so you take a certain attaching sphere, and you just isotope the attaching sphere. Okay, so the procedure in terms of attaching handles is very simple. So what you do is you just consider an isotopy So for T 0 to 1, this is an isotopy of embeddings such that psi 0 is the original psi. Okay, and this isotopy will also give rise to an isotopy of framed embedding. So if the first one is framed, then you can use the isotopy to transform the framing, to transport the framing all the way to the last one. So the point is that you obtain a psi1, which is going to be another embedding. This is going to be a framed embedding. And then you can attach a handle using this attaching sphere. So this gives rise to another handle attachment. Okay. But it's, I mean, it's a simple problem in differential topology to note that if you take an isotopy of these embeddings, then the manifold that you obtain is diffeomorphic to the manifold that you obtained with psi1 is diffeomorphic to the manifold that you obtained with psi0. So we don't change, this process doesn't change the diffeomorphism type of xi. Okay, so that's not very hard to see that, you know, you can get a diffeomorphism from one to the other. But I guess the point is that the thing that's interesting is that this new handle attachment can be obtained from a different, directly from a different gradient-like vector field. So the point is that there exists a gradient-like vector field v tilde for the same function f, such that the attaching map induced by v tilde is psi1. Okay, so if you look at the unstable manifold of v tilde, you're going to get psi1. And how do you do that? Well, this is kind of, you know, a little technical and not particularly enlightening, but I'm going to draw a picture and then maybe you can fill in the holes, or you can look at Milner's book or Matsumoto's book to get all the details. But, you know, say that this is your xi minus 1. And then you attach a handle. And your attaching sphere is over here. It's this red thing. And say that your V, you know, your gradient-like vector field, it goes like this, goes along here, and then it does something like this. And here's the critical point. That's the original picture. And the orange thing are the flow lines of V. Okay. So what does it mean to do a handle slide? It just means that, you know, I take an isotopy of the attaching sphere. So let's say I'm going to move this red dot a little bit to the right. So say that my isotopy moved this red dot from here to here. Okay. So then what do I do with V? Well, I'm going to look at a little neighborhood of that in xi minus 1. And then I'm going to keep the V constant equal below that. And then here, I'm going to use this isotopy to kind of change my V. Okay, so I can do that with a bump function. So that outside a neighborhood of that, I actually obtain the same below here, I have the same V. I only really want to change it in a neighborhood of where I'm attaching the handle. Anyway, it doesn't matter very much, but the point is that a handle slide can be represented by just taking another gradient-like vector field, and the Morse function doesn't change. You can do that without changing the Morse function. Okay, any questions about this? Yeah, so we can perform handle slides. You know, I showed you last time, you know, one kind of fun thing you can start doing is you can look at just surfaces. You know, I put a say I do this Möbius band, and then I have another handle here, and then I can actually try to slide it, and I can slide it around this other one handle, and then when I do this, you know, it's kind of fun because then when I do that, then I'm gonna have here's my original guy, and then this is gonna go here, and it's gonna be another non-orientable handle like that. Okay, so that's one thing that you can do for fun. Actually, by the way, you know, this now if you just cap with a disk, then you have a Klein bottle. But anyway, this is just an example of handle slide, and it gets more interesting in higher dimensions. I'm going to talk about that a little. I'm going to give some examples later when I talk about 3 manifolds, like what exactly it means to do a handle slide there. But I mean, if you just do a little handle slide that doesn't, where you don't interact very much with other handles, maybe you don't gain very much from a handle slide, but it's kind of cool when you do this handle slide kind of along another handle. So, you know, I think, of course, after you attach the first handle, then maybe you're like, oh, I don't know what's the handle anymore, because now, you know, I thickened it and I'm at a different level. But you can sort of not, you can still kind of try to remember where the last handle was, and you can try to slide one handle over the other handle. Okay, and you can certainly do that. Okay, so let me say, so actually what you're doing here is the following. So you can think of it like this. So if this would be your point pi minus 1, and this is your pi, what you're doing is sort of, you have your attaching sphere of pi, which is, let me draw in red, these 2 points. And a handle slide is an isotopy of this attaching sphere. So as if you're just isotoping a little bit, it doesn't change very much. It doesn't change. It doesn't change the picture very much. But what's actually interesting is when you go through another, like say you go through another one handle, and how can you see that in terms of the attaching sphere? So what's happening is that basically this attaching sphere is crossing another. It can't cross the attaching sphere of this guy because the attaching sphere of this guy is now in the interior, but it crosses the belt sphere of this guy. So the belt sphere is this sphere right here. So basically, what happens here is that the attaching sphere, which is this guy, this attaching sphere, crosses the belt sphere, which is the Sn minus k minus 1. So this belt sphere. And when that happens, then it creates interesting topological changes. I mean, it doesn't change the diffeomorphism type of the manifold, but it changes, for example, the topology of this diagram. And as you'll see, maybe in dimension 2, this is not, it's not that interesting, but in dimension 3, and especially in dimension 4, but even in dimension 3, this procedure of handle slides, when you slide one handle over another handle of the same dimension, that's going to create very interesting transformations of the diagrams. Okay, maybe this will be clearer when we have sort of the higher dimensional examples. Okay, so now let's talk about switching the order of handles. So switching the order of handles. So we'll see the significance of handle slides a little bit more later. But maybe, yeah, so the proposition that I'm gonna sort of not 100% prove, but sketch the proof of is the following. So so suppose you fix the Morse function on a closed manifold as above. So as above just means where each critical value corresponds to a unique critical point. Now suppose that the index of P minus 1 is bigger than or equal to the index of Pi. Then basically what I'm going to claim is that I can switch the order of Pi and Pi minus 1. Okay, so then there exists a Morse function, f tilde, in infinity of x, such that the critical points of f are equal to the critical points of f tilde, and f of p f tilde of pi is equal to f of pi minus 1, and f tilde of pi minus 1 equals to f of pi, and f equals f tilde in outside of the interval ai minus 2 ai. Okay, so maybe let me draw the picture. So here's my manifold X. Well, so here is Pi. Here's Pi minus 1. Here's Pi. And here's the rest. So what I'm saying is basically I can switch the order of Pi and Pi minus 1. And I can consider that I can change this Morse function to another Morse function that's going to take the Pi minus 1 up here and the Pi down here. And it's going to keep the same, it's going to keep everything equal outside of these two handles. Okay? But I'm assuming that the index of Pi minus 1 is bigger than or equal to the index of Pi. Before I sketch the proof, let me just say the easy consequence of this. So the corollary of this is that there exists a Morse function, f, with critical points P1 through Pn, such that they are, ordered, and the indices are in increasing order. So the index of P1 is less than or equal to the index of P2, is less than or equal to, etc. Okay, so the corollary is that I can find a Morse function such that the critical points, they come in increasing order of indices. So I don't have to worry about later attaching a one handle if I've already attached two handles. Okay, so I can start with all the zero handles, then I can add all the one handles, then I can add all the two handles, and so forth. Okay, so I can always find a Morse function like that. But this is going to be good in terms of when we want to construct manifolds, when we want to classify manifolds. Okay, any questions about this before I give a sketch of the proof? No? All right, so the most important idea in the proof is actually looking at how the belt sphere of Pi intersects the attaching sphere. The belt sphere of Pi minus 1 intersects the attaching sphere of Pi. So I want to look at the attaching sphere of Pi. So I have to choose. So let me. So proof. So fix a gradient like vector field for f. Okay. So then you look at the unstable manifold of Pi intersected with the pre-image of ai minus 1. So remember, ai minus 1 is this level here. Okay, so this is called the attaching sphere of this handle. And let's yeah, let's say K is the index of Pi. So this is going to be an SK minus 1. Okay, and then I'm going to look at the what's called the belt sphere of Pi minus 1. So this is an Sn minus, well, let's say that J is the index of Pi minus 1. So N minus J minus 1. Okay, so the point is, can these two spheres intersect? And I claim that they cannot intersect transversely or they can only intersect transversely if they don't intersect. And this is because of this assumption. So we assume that the index of Pi minus 1 is bigger than or equal to the index of Pi. So J is bigger than or equal to K. So this implies, with a small little calculation that I think you can all do at this point, that this Sk minus 1 intersects Sn minus J minus 1 transversely in this per-image of Ai minus 1, if and only if they don't intersect. Okay, so up to a small little handle slide, if I just perturb, if I take a little isotopy of this guy, that corresponds to choosing another gradient-like vector field. So up to a handle slide, we can assume that these spheres don't intersect. Okay? So then that means basically, the picture that I'm going to draw is like this. So you have your Pi, you have your Pi minus 1. So here is your sphere. Here's the unstable manifold, and here's the stable manifold of one. Here's the unstable manifold, and here's the stable manifold of the other. So they don't intersect in this. They don't intersect in this level, so they won't intersect at all in this whole region because of the flow. So that means that if you take this and you intersect with the whole pre-image of Ai minus 2 Ai, this does not intersect, doesn't intersect. The stable manifold of Pi minus 1 intersected with the pre-image of Ai minus 2 Ai. Okay, so now when we have this picture, now we can actually change the function as we want. So basically, now we can choose a way to deform the original Morse function to some f tilde, which is going to lower the value of this guy to whatever we want and increase the value of Pi minus 1 to whatever we want. We can actually end up with an f tilde where f tilde of Pi and f tilde of Pi minus 1 are any numbers that we want between Ai minus 2 and Ai. So if we fix A and B in Ai minus 2 and Ai, we can find an f tilde such that f tilde of Pi is A and f tilde of Pi minus 1 is B. Okay, so we can do that, for example. Yeah, so you can choose you can just basically choose an increasing function of the interval Ai minus 2 Ai into that, and you can choose a family of such functions that's parametrized by, I don't know, some parameter that, I don't know, say equals 0 in the neighborhood of this guy and equals 1 in the neighborhood of this guy. Anyway, this is the kind of like a calculus exercise now. But you can only really do that if these two don't intersect. Okay?
Sorry, can you draw an example where they intersect?
Yes. So an example where they do intersect is if you take your torus that's vertical like this, and here is your pi, and here is your pi minus 1. And when you look at this level here, you see that your this unstable manifold is this guy, and this stable manifold is this. They do intersect here.
Okay.
Yeah. But you see that if you perturb it slightly, then they won't intersect anymore.
Like you can move one down and one up.
Yeah.
Okay.
So if you perturb slightly, I mean, you can perturb with Morse function if you want, but you could do it without even perturbing the Morse function, just perturbing the vector fields. But
Okay.
perturb the Morse function, then now the flow lines will go like this. To the back, and then this guy, I don't know, goes through the front. And this guy goes like this. And they don't intersect anymore.
Thank you.
Mm-hmm. Okay, so let me say this one more time. So if you, if they don't intersect, then now you can actually define, a reparametrization of this interval AI minus 2 AI. So you can kind of find a family of diffeomorphisms of increasing functions from here to here. So family of diffeomorphisms, and you apply that to F. But sort of this parameter is going to change as you move here, and maybe sort of when you look at this level pre-image of AI minus 2, when you get near the intersection with this unstable manifold, then I mean you have a certain parameter, and then when you get near this guy, you have another parameter, and you just have to kind of find something smooth from one to the other. Okay, so if you want to fill in the details here, that's a good exercise. Or if you can't do it, you can look at Milner's book or Matsumoto's book. Maybe it's not so hard to see that you can do it. Okay, so that's called moving handles. So you can move handles up and down, provided that you have this condition. So at the end, you can always assume that you have a Morse function, F is Morse, such that the critical points have increasing or non-decreasing indices. So such that the critical points are like this, ordered by F, and the indices are non-decreasing. Okay. But you can actually do more. We can actually do more. So this proof, I mean, I proved a little more than I stated at first. I actually could have pi and pi minus 1 be at the same level. So we could, if we wanted, we could change the Morse function to not have that condition, but to have the following condition. We can actually do more. We can assume that all index k critical points have the same value. So this kind of is not the kind of Morse function that we were treating before, but this is just a comment that some people talk about when describing manifolds. So you can actually, so you say you start first with your zero handle, or all the zero handles at the same critical value. Then you can attach all the one handles at the same time with the same critical value. And then you can attach all the two handles at the same time with the same critical value. Okay, so that's that's not the kind of Morse function that we usually like, but sometimes people like these kinds of functions because they can just say, if I take in this one level where when I go through this one critical value, I attach all the index 1 critical points at the same time. So you can do that. There's no problem. Like for example, this would be if A equals B. Okay, and people sometimes like to even be a little funnier about notation, particularly for three manifolds, but it could be for anyone. You can say that F is a Morse indexing, no, a self-indexing Morse function if for all the critical points in the pre-image, so if P is a critical point, then the index of P is equal to the value of the function of P. This is a funny definition, but it just means that you have a Morse function where at the value 0, you have all the index 0 critical points. At the value 1, you have all the index 1 critical points. At the value 2, you have all the index 2 critical points, and so on. Okay, and based on this argument that I gave you, you can always find a self-indexing Morse function. Okay, so we're going to use these self-indexing Morse functions to talk about three manifolds and maybe a little bit about four manifolds, but let's not talk about them more. But maybe it's a cool thing to see that they always exist.
Isso é meio que uma tentativa de recriar a ideia de função altura, né?
Mais ou menos, é. Mas assim, é uma ideia de você dizer basicamente que você pode colocar todas as alças de uma dimensão ou de um índice ao mesmo tempo, que elas não, você pode sempre supor que elas não interagem entre si, né? Porque você sabe que você pode colocá-las uma de cada vez, mas por causa dessa condição, né, que o índice é maior ou igual que o índice do outro, você pode, na verdade, trocar ou, na verdade, colocá-las no mesmo nível. E você pode sempre supor que uma alça não está adjunta a uma outra alça, né? Que elas todas são adjuntas a uma coisa abaixo. Isso tem bastante relação com o fato de que no complexo celular você pensa que uma célula está sempre adjunta a um complexo celular de dimensão menor. Você em geral não adjunta uma célula a uma coisa que já tem uma célula. Você adjunta todas as células de dimensão 1 ao mesmo tempo no complexo de dimensão 0, e assim por diante. Mas a princípio você poderia definir um complexo celular onde você simplesmente adjunta células ao que você tem embaixo, independente se você tem células daquela dimensão ou de dimensão maior. Mas aí você consegue mostrar como uma utopia que você consegue desfazer isso. This is a comment for someone who asked me about cellular complexes last time. Okay, so let's continue and let's talk about one more amazing transformation that we can do with handles, which is called handle cancellation. So handle cancellation. Handle cancellation is actually marvelous. It's even more interesting, more beautiful than handle moves. So handle cancellation is the following. So maybe I'll call this a theorem. And it says the following. Suppose f as above. So f. So as above, I'm not allowing this kind of behavior anymore. So I mean that every critical level corresponds to a unique critical point. Every critical value is the image of a unique critical point. And suppose that we have pi minus 1 and pi critical points such that the index of pi minus 1 is equal to the index of pi minus 1. So they have adjacent indices. And that when you look at the unstable manifold of Pi, actually we have to fix a gradient-like vector field. The gradient-like. So you can talk about unstable manifolds. So when you intersect this with the stable manifold of Pi minus 1, and you look at a level, you cut it, that this is a unique point. This is a unique point. So suppose that they intersect the belt sphere of Pi minus 1 and the attaching sphere of Pi intersect at a unique point. Then these handles can be canceled. So then there exists a Morse function, another Morse function, such that f is equal to f tilde in outside of these two handles, so in the preimage of ai minus 2 ai, and, no, sorry, not in, outside. And f tilde doesn't have critical points in this interval. So I can draw the picture again. So now the picture is as follows. So if this is Pi minus 1 and Pi, and if my attaching sphere of Pi intersects this guy at exactly one point, it's the same. This is the same thing as saying that there is a unique flow line connecting Pi minus 1 and Pi. Then these critical points can be canceled. And then we just have something with no critical points. Okay, so that's the theorem. So let's try to prove this. I mean, I'm not going to prove it. There's a key lemma that I'm not going to prove, but I'll kind of explain how you can do this. Okay, so first of all, let's say that K is the index of Pi. So K minus 1 is the index of Pi minus 1. So we know that basically by the Morse lemma, there exists a chart. So near Pi, we can write f as, well, I'm going to just write directly the vector field. We can write the vector field, the gradient-like vector field, as minus 2 x1 ddx1 minus etc. minus 2 xk ddxk plus 2 x1 xk plus 1 ddxk plus 1 plus 2 xn ddxn. And at k, yeah, and at p minus 1, I can do the same thing, but with one less negative sign. But actually, I'm gonna tweak things a little bit, and I'm gonna change the order of the coordinates in such a way that, actually near Pi, v is going to be plus 2 x1 ddx1. Actually, no, let's just keep it like this. No, I don't want to confuse you more. So near Pi, I can write it like that. And near Pi minus 1, if Pi minus 1 goes to 0 and Pi goes to 0, I can write v as minus 2 x1 ddx1 minus, and then I stop at k minus 1, d dx k minus 1, and then plus, so I changed this sign of s, k, and so on. Okay, so that's just a Morse lemma. I mean, basically the definition of a gradient-like vector field adjusted to with the extra condition that I put today. Okay, but now there's a lemma, which I won't prove. It takes about, I think, 12 pages in Milner's book, but it's not very hard to believe, but it's actually the key of this canceling handles. But I won't do the details here. But the lemma says that you can actually find if you have a unique trajectory connecting pi to pi minus 1 to pi, then you can find the neighborhood of pi and pi minus 1. So there of this trajectory. So there exists a neighborhood of the unique trajectory connecting pi minus 1 to pi, and the map, so there's a unique neighborhood u, and the map phi from u to Rn, such that, so in this map, so that the map basically takes pi minus 1 to the origin, and it takes pi to the point 0, 0, 1, 0, 0, where the 1 is in the kth kth number. So this is sort of ek, the kth element of the basis of Rn. Okay, such that now my vector field V has the form minus 2x1 ddx1 minus etc. xk minus 1 ddxk minus 1. And then I have a function of xk. I'm going to call v of xk ddxk. And then plus blah, 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 plus xn ddxn. Where this v of xk is a function that basically switches from being like xk, like minus xk, to being like xk. So this function v of xk is equal to 1 near 0, and v of x, sorry, it's equal to xk near 0. And it's going to be equal to 1 minus xk near 1. So it's something that looks like this near 0, and then it looks like minus near 1. And moreover, this function is always positive in the interval 0, 1. So it doesn't have any other zeros. Okay, so this is the tricky lemma, and to construct this, you have to really work with some patching. It's not very hard, but it's a little tricky. And I'm not saying very much about the Morse function itself. I'm just talking about the gradient-like vector field. Okay, so it's something that you can reconstruct. Maybe you can prove this yourselves, or you can look in Milner's book. But that's the procedure. So then, is this clear? What I'm saying? So I get a neighborhood of this trajectory. Such that this gradient-like vector field has this expression. Okay, now what I do is I just homotope v to a function that doesn't have any zeros. So now you homotope homotope v to a v tilde that looks the same, but with a function v tilde. So v tilde is minus 2x1, ddx1, etc. And then you have 2 vk tilde of xk, ddxk, and then plus etc. and then 2xn ddxn. But this vk tilde now doesn't have any zeros. This vk tilde of x of k is now always less than 0 for xk in 0, 1. Okay, so here's my vk tilde. Sorry, not vk tilde, v tilde. Okay, so what I did is I homotoped my gradient-like vector field to another vector field that doesn't have any zeros. Okay, so you can do that. Okay, so maybe, you know, there's one more thing. You can do that actually in the neighborhood of any flow line. It doesn't have to be a gradient. It doesn't have to have the property that's a unique flow line. But now you're going to use the uniqueness to be able to reconstruct a function out of this vector field. So now, you know, you have your neighborhood, U, which used to be which is the neighborhood of that original flow line. But now you constructed another vector field, v tilde, that doesn't have any zeros here. So v tilde doesn't vanish here. So now what you want to do is you want to use this v tilde to construct a function f tilde. So what do? You basically just integrate v tilde. But you have to be a little careful because sort of the value of the function here is going to be, well, actually the v tilde goes up. So the value of the function here is going to have to be higher than the value of the function here. And this maybe is also another kind of tricky spot, tricky point. And for this to really work, you cannot have, the function cannot have another flow line that goes like this, that goes outside this neighborhood. Otherwise, you're going to have a problem because the value of the function here will already be determined by this. So you use this v to define the value of the function, but you need there not to be another connecting, another flow line connecting this point to this point. Okay, so there are some details here that need to be filled in, but the point is this. Maybe what you need to remember is that if you have two adjacent critical points two critical points with adjacent indices, the smaller one is k minus 1 and the upper one is k, and there is a unique flow line connecting one to the other, then you can cancel these two. You can find a new Morse function without critical points there. So let me give some examples. So any questions before I talk about some examples?
Então, você integra o V-til para construir F-til, é isso?
É, você integra o V-til para construir F-til, exatamente.
Ah, tá, tudo bem.
Okay, now you have to be a little careful, you know, because the value of the function is already determined on the boundary of this neighborhood. But yeah. All right, so here's some examples. So the first one is, I don't know, say that, so if you have, we can do this in dimension 1 or dimension 2, but in dimension 1, so if you have this and this, when you look at the unstable manifold of this point, the stable manifold of this point, they intersect at a unique point. Or if you think about it, you know, there is a unique flow line from this guy to this guy, which means that you can actually cancel these two. So canceling these two means, first you find a vector field that will just do this. And then you use the flow of this vector field to change the Morse function, which means, after this change, the Morse function you're going to end up with is something like this. So basically, you're just increasing along this flow line. You're no longer decreasing. So you're going to go like this and not have any critical points anymore. Okay? And you can do this in 2 dimensions too. So, or even that heart that I drew before. You can look at, I don't know, this pair of points. And you see there's a unique flow line from this point to this point. So you can do the same thing. You can look at a neighborhood. So now I'm kind of in dimension 2. But it doesn't actually matter. Like when the other dimensions don't do anything. It's just there's one direction where you change from minus to plus. And that's the direction. So you look at the neighborhood and then you substitute this by a vector field that's going to go like this. And then you use this vector field to modify your function and to get a function with no with no critical points in this neighborhood. Okay. And so one more thing, I mean, I didn't do it very precisely here, but when you homotope, of course you homotope in an even smaller neighborhood of this gradient line, because you want them to equal outside of this neighborhood, so you have to do some bump function. Okay, so here's another example. But in particular, a corollary of this is that there always exists a Morse function with a unique index 0 critical point. And why is that? That's because I'm assuming the manifold is connected. So if I have several index 0 critical points, say I have more than one, then remember, first I can find a Morse function where all the index 0 critical points all the 0 handles are attached first, and then I have the 1 handles. But then each 1 handle, the unstable manifold is going to be just one manifold. It's just going to be an interval. So if it connects, if it connects different, if it touches different index 0 critical points, then I can always cancel one of them with the 1 handle. So the only situation where I can't cancel is if I have a 1 handle that's attached over the same index 0 critical point. And basically, because S0, because Sk is connected for k bigger than or equal to 1, the only way to connect index 0 critical points is by using 1 handles. So if I use higher dimensional handles, I cannot connect index 0 critical points. So that is going to imply that I can always cancel all the index 0 critical points, all the 0 handles, except for 1. Okay, so let me say this argument once again. So suppose I had several index 0 critical points, so several 0 handles. Then I claim that I have to have a 1 handle connecting them. And because two handles and higher dimensional handles, the attaching sphere is connected, so I cannot connect things that start disconnected. So that means I have to have 1 handles connecting these guys. And each 1 handle that connects 2 different guys is actually going to cancel with that 0 handle, because there's a unique flow line connecting that. Okay, and then here again, it's going to cancel. So you can cancel all the 0 handles except for 1. Okay, any questions about this? Is this getting too impressionistic? Are you there? Are you there?
Sim, sim.
Sim, estamos aqui, meu.
Tá muito o quê?
Estamos aqui, mas tá ficando complicado.
Okay, can you ask a question, or what are you struggling? Maybe I can speak more slowly, but maybe you can say one thing you didn't understand, so I can repeat.
Eu me perdi bem no começo, assim, já. Então, eu tive que sair um pouco na aula e eu acabei me perdendo. Por isso que talvez eu não esteja acompanhando.
Tudo bem. Bom,
Mas
então
vou reassistir.
Tá, a última coisa que eu falei, né, aqui é que você pode cancelar dois pontos críticos, onde a diferença de índice é 1, e você tem exatamente uma linha de fluxo de um vetor tipo gradiente, exatamente uma que conecte um ao outro. Okay, so you can cancel two critical points that have adjacent indices and a unique flow line from one to the other.
A ideia que você está fazendo é construir operações entre esses attaching handles para acabar indo para uma combinatória, né?
Eu estou tentando simplificar, exatamente. Estou falando, se eu começo com uma função de Morse qualquer, isso aí vai me dar uma handle attachment muito complicado, e eu posso ir fazendo operações para melhorar, para fazer uma coisa mais simples.
Uhum.
E no final, né, at the end, the conclusion is that if X is a manifold, a closed manifold, you can always end up, there exists a handle decomposition, so it's a closed and connected, I'm always assuming connected. There's a handle decomposition where you start with a unique zero handle. And then you attach all the one handles, then you attach all the two handles, etc. Okay? And actually, you also can assume that there is a unique top dimensional handle. And why is that? That's because given a Morse function, you can basically, given a manifold, you can turn a manifold upside down. So why can you do the same thing? Well, if you are given a function f, you can look at the Morse function minus f. And the critical points are going to be the same. But the Morse indices, they get switched. So the Morse index of p with respect to f of minus f is going to be n minus the Morse index of the function of the point p with respect to f. So, this is, if I take a surface and a Morse function and I switch the sign of f, then what used to be an index 0 critical point is going to be an index 2 critical point, and so on. So the indices get switched with an n in front. So that means that the index 0 critical points of minus f are the index n critical points of f. Okay, so basically, if I start with a Morse function, I can cancel all the zero handles, all the index 0 critical points except for one, and then I can switch the sign of the function. I can do minus f, and then now all the n handles are now 0 handles. So then I can cancel all of them except for one, and I can turn it back. So that means I end up with a unique n handle and a unique 0 handle. Okay, so that's the conclusion.
Todas as operações são feitas na função, não é?
Quase todas, né? O handle slide não precisa mudar a função, né? O handle slide você pode só mudar o gradient-like vector field, né? O campo vetorial.
Tá.
But the other operations you change the function to. But in a way, both the function and the gradient-like vector field are just auxiliary. What you really care about are the handles. So using this, now it's a lot easier to try to describe all surfaces and to describe all three manifolds and all four manifolds. So today, let me do the classification of surfaces again, and with these operations in mind, I think it will be easier to understand. So let's now talk about surfaces. So with these operations in mind, with all that I said, how do you build a surface? Well, you start with a zero handle, which is a disk, and then you attach a number of one handles until the point where you actually have, you need to have the boundary of the remaining thing be just one connected, and then you can close up with just one index 2 handle. So, how do you build a surface? So you start with a disk. So this is your unique zero handle. Then you have a bunch of one handles. And then you end up with a 2 handle. So every surface can be constructed like this. Okay, so a zero handle for me, it's a disk. So I can start with a disk. And now I have to attach one handles along the boundary of the disk. And we've seen that, basically, how can you attach a one handle there? You have to choose an S0. And then there are two ways, basically, up to diffeomorphism. You can either attach, it's the two possible framings. So either you attach them like this, or you attach them like this. And the point is that one of them, after attaching a one handle, one of them breaks the boundary into two, and the other one does not break the boundary. So this one, which I guess you can call the orientable one handle, it's going to take the boundary and it's going to split it in two. And the non-orientable, so this one changes the number of connected components, or increases the number. And the non-orientable one handle does not. Okay, so that means that if I start with a disk and I attach a orientable one handle, I can't just close with the two handle because I have too many boundary components. So if I have this, if I attach one orientable one handle, then I have to attach another one handle before I can close up with a two handle. Otherwise, I just have to put two handles, and then that's not good. So then you have to argue that basically if you continue attaching orientable one handles that don't cross each other, then you're just going to increase the number of connected components of the boundary, so you can never get to just close up with a two handle. So you have to start intertwining them. So the moment if you have a one handle and then you intertwine with another one handle that that's orientable in the same way, then that actually is the same as doing something like this, and then you can actually close up with a two handle, and then you get the torus. And you can check that if you add a number of orientable one handles, if at the end you have one connected component, then you can reorder them so that you actually have G versions, G times this procedure here. So if you have, if you attach, I don't know, n orientable one handles such that the boundary is connected, then m has to be even, m has to be 2g, and you can actually you can do some handle slides to end up with a situation that's just like this: blue, blue, intertwined, with red, G times. And the surface after you cap with a disk is going to be exactly the genus G surface. So this, the genus G surface. And you can also check that if you just put one handle that's not orientable, then sort of you mess this all up, and basically, if you just put, this was one of the exercises from last time, that if you just put one non-orientable handle, then now, if you basically, no matter what you do now, if you end up with a connected top, you can always rearrange so that you're always adding these non-orientable handles that are not intertwined. So if you just have one non-orientable handle, then you can basically use this handle to do a handle slide of all the other handles and make them non-intertwined at the end. So this is going to be at the end up to after a bunch of handle slides. This will, no matter how many handles you attach, you can later attach, it's equivalent to attaching a number of non-orientable handles. So K non-orientable handles. So this is basically, so you start with your disk, and then you attach, here's one, then you attach two, and then you just attach K. Basically, you attach K Möbius bands. You cut a little bit of the Möbius band and you attach it. Okay, so you attach K non-orientable handles, and at the end, you close up with a disk. So this is the same as taking your RP2 and doing K copies of it, the connected sum of K copies of RP2. Okay, so maybe just to give a little light into this thing, which maybe is a very important part, is let me just do this exercise in the simplest possible case, and maybe if you understand that, then you're going to be inspired. You're going to understand that in general. But you might ask, so what happens if I just do like a little non-orientable handle? I put the non-orientable handle here, and then I put two orientable handles. So say I put two orientable handles, like I'm trying to do another torus. So I put something like this, and then I put an orange one. Like this. So are you saying that this is the same as doing three non-orientable handles? And the answer is yes, that's what I'm saying. So how do you do that? You need to do some handle slides. And this is, can get kind of pretty. So let's see what happens. So what happens is you have to use this blue handle to kind of make the other ones switch. So what I'm gonna do is I'm gonna take this orange guy, and I'm going to go through this handle and see what happens. So if I go like this, I end with it like here in the middle. And then, actually, I'm not going to do this because I haven't prepared it. But my advice to you is do this case first. And then if you understand this case, if you understand how you can get from here to a picture where they don't intertwine, now they turn into, they will turn into this. Using handle slides, you can separate them, and you can these are going to be 3 non-orientable handles attached separately. And this is showing basically that if you take one RP2 and you take the connected sum with a torus, that's the same as doing an RP2 connected sum with an RP2 connected sum with an RP2. And by the way, this is the Klein bottle. Okay, so that's it, and this is the classification of surfaces. So all the surfaces are either, so all surfaces, closed surfaces, they are either the orientable genus G surface, which is the connected sum of G tori, or they are the non-orientable NK, which means just the K copies of RP2. And that's it. And I mean, you have the empty connected sum, which I guess you define to be just S2. And then you have S2 separately. Okay. So, all right, any questions about this?
Eu tenho duas, na verdade.
Sim, fala.
A primeira é, tem alguma referência onde tem essa classificação usando handles? Eu tentei achar, não consegui.
Deixa eu pensar. Eu não sei, deve ter. Eu não sei. Isso aí eu meio que aprendi sozinho, aprendi em aula. Eu não lembro disso sendo explicado num livro. Mas, assim, eu realmente acho que se vocês entenderem tudo que eu estou falando aqui, vocês conseguem reconstruir essa demonstração.
Então, tudo bem. E a segunda pergunta era a seguinte, acho que é meio bobo, mas, tipo, o que a gente acabou de fazer, essa classificação, ela não mostra, por exemplo, que a superfície de genus G não é difeomorfa à superfície de genus G', onde G é diferente de G', né? Ou mostra?
Você precisa de um pouquinho mais, na verdade.
Ah, tá.
Você precisa, por exemplo, da característica de Euler. Se você deixa eu pensar. De repente você consegue. Eu imagino, eu acho que dá para mostrar de uma forma mais explícita, com a definição que a gente teve da característica de Euler, que a característica de Euler vai ser, desse daqui vai ser 2 menos 2G, e desse daqui vai ser 2 menos K. Então, na verdade, você classifica a superfície só sabendo a característica de Euler e sabendo se ela é orientável ou não. Se a característica de Euler for ímpar, ela tem que ser não orientável. Yeah, so to be able to compute the Euler characteristic just based out of these connected sums, maybe you have to say a little bit more, but I don't think it's a lot hard. I mean, there are different approaches, but you can, for example, last time I said that from the handle decomposition, you get a cell decomposition. So if if you take a generic gradient-like vector field, then these, and you order the critical points as I told you, then the unstable manifolds will in fact give you cells. And the center of the cell is the critical point. So basically you probably know that the Euler characteristic is the number of cells of each dimension, but when you alternate signs. Basically here, it's the same as the number of handles. So you can basically, the Euler characteristic is the number of -1 to the k times the number of k handles. Okay? Então aqui, por exemplo, né, você tem, para cada um desses toros, você tem duas dois alças. Now, for each one of these tori, you have two 1 handles. So you have 1 0 handle, 1 2 handle, and you have two 1 handles for each genus. So that's why you get 2 minus 2G. But for the non-orientable one, for each non-orientable handle, that's 1 copy of RP2, basically. So you have K of them. So at the end, you have 1 plus 1 minus K. Okay? So, but I'm using a little bit of algebraic topology. It's not self-contained in this course, my explanation. Ok.
Tudo bem.
Beleza?
Daria para fazer com cohomologia também, né? Por exemplo, usando sequência de Mayer-Vetóis ou alguma coisa assim.
Daria para calcular a característica de Euler ou para mostrar que elas não são diffeomorfas. Sim.
Não, tudo bem. Obrigado.
De nada. Okay, I think I'm not going to talk about 3 manifolds today because there's not enough time. So tomorrow we will talk about 3 manifolds, 4 manifolds, and we'll talk about the H cobordism theorem briefly. Okay, so just to give you a quick idea, so describing a surface is basically just you have the circle and you describe the handles. But if you want to go to 3 dimensions, you have to look at 1 and 2 handles, so it's a little bit more complicated. And if you look at 4 dimensions, then you have to look at 1, 2, and 3 handles. But the cool thing is because 3 and 4 manifolds are still pretty close to our world, we can still visualize them and draw diagrams to see how these handles attach and describe all manifolds of dimension 3 and 4. At least the orientable ones. So I think for dimensions 3 and 4, I'm going to restrict myself to orientable manifolds. Because it's hard enough and it's interesting enough. Okay, so let's end right here.